This section we're going to look at solutions. To start off with, we're going to discuss what the difference between a mixture and a solution is, some terminology that goes with solutions, different types of solutions. And when we think about a solution, we usually think of, oh, I dissolved something in water. Well, that's not the only type of solution out there. And then we'll look at some of the thermodynamics involved with making a solution. All right, so let's start off with types of mixtures. All right, so we can get a suspension, a colloid, or an actual solution. Okay, I've got some pictures of some different solutions up here, but before we discuss the pictures, let's take a look at what, describes these types of solutions in a particulate view. So when I think of a suspension, I'm thinking of an actual mixture. These are things where I can see the different pieces a lot easier too. Okay, so things like muddy water, we can see those different pieces. Now, what marks this has a lot to do with the size of the particles. So in a suspension, the particles are large. All right, and they are typically greater than 1,000 nanometers. Okay, when I talk about colloids, these are starting to get smaller in particle size. And sometimes we might not always be able to see the particles with our naked eye. Okay, these are medium particles. And we're going to get somewhere between 2 and 1,000 nanometers is our particle size. And then our true solutions are homogeneous mixtures where we cannot see any difference between the particles in there. These are going to have tiny particles. Right? And they're going to be less than 2 nanometers. Okay? And so we can't see those particles. Now this is an interesting solution right here. So I've got two different solutions. I have a true solution and then I have a colloidal solution. Now, when I shine a torch through, you can't see any difference in the particles. There's no light scattering in a true solution. But that colloidal solution that has particles on that smaller end, you can see where that light beam goes through. Okay, now we can see a difference between our particles. So you have an idea of what the particle size just looks like. There you go. So the first bottle here, we've got 2 nanometer particles up to the last bottle with 200 nanometers. So we go through from something that looks like a true solution, all right, you can't tell any difference, to that 200 nanometer particle where it's cloudy. You know that there's more than one thing mixed there. And then my top picture here, there are certain mixtures that don't look like anything until you put them under a certain kind of lighting. So these particular mixtures, you can't tell that there's anything in them until you shine them under UV, and then they're UV reactive. They fluoresce under ultraviolet light. Okay, so there's all sorts of interesting things that happen with mixtures. Now I want to talk a little bit more about colloids. Even though the focus of this unit is on solutions, I do want you to understand the difference between a colloid and a true solution, besides this picture here with the light scattering. Okay, we actually have colloids all around us. Okay, aerosols, solid aerosols, emulsions, foam, solid emulsions. Okay, let's look at some examples of these. All right, so here's a picture of an aerosol. Okay, an aerosol is a liquid suspended in a gas. An example is fog. All right, so I actually took that picture on a foggy morning up at my aunt's house in Northern California when I went there one time for Thanksgiving, and it unexpectedly snowed overnight. And so the weather was kind of weird, and so the next morning when the sun came out, we ended up with a lot of water vapor that was escaping there. So aerosols are liquid and gas. A solid aerosol, an example is smoke. So this is a solid suspended in a gas. All right, so smoke has all sorts of little particles that are in it. All right, and so you can see that big black cloud there. It's not just gas that's the black. A lot that black stuff is typically going to be all of the little particulate matter that gets burned up and then suspended in the air. Okay, an emulsion. All right, here's a picture of an emulsion. Mayonnaise. So mayonnaise, if it doesn't have an emulsifier, it separates out. So there's lots of things that we need to emulsify in order to get it to be smooth. And so an emulsion is a liquid in a liquid. All right, and so we get that separation there because of that oil. And so egg is a good emulsifier. Egg will keep that oil suspended in there. And so the example here is that mayonnaise. All right, foam is a type of colloid. Whipped cream is my example here. This is a gas in a liquid. Example being whipped cream. Whipped cream is cool. So if you've ever made whipping cream, you get your heavy whipping cream and then you use your egg beater and that whips a whole bunch of air into it. Or if you've got the aerosol canister, then that'll force that to go together. And so, if you put your whipped cream out and then you leave it sit there for a while, it collapses, right? And that's because eventually the gas starts escaping and you just end up with the liquid left. So your nice fluffy whipped cream is because you've put a lot of gas, usually air, into your liquid there, the heavy cream. All right, and then my last one here is a solid emulsion. That's an opal there. A solid emulsion is a liquid in a solid. And so the opal, all the shiny stuff that you see in an opal is because there's liquid trapped in there. And so you're catching all the refraction of the liquid. All right, so that should hopefully help you understand our colloids a bit better. All right, now let's switch back to solutions. All right, when we look at solutions, we need to understand some different terminology. All right, we've got lots of vocabulary that we need to understand as we study our sciences. So, solution. What is our definition here? A general term for a solute dissolved in a solvent. Okay, or a homogeneous mixture of two or more components. In which particles intermingle at the molecular level. Okay, so again, the key thing there is it's a homogeneous mixture. I can't tell the difference between my solvent or my solute. It's all mixed together uniformly. All right, and what's my solvent? Usually that's what we have in the greater quantity, so the component of a solution. That is the greater quantity. All right, and then the solute is usually the one that's there lesser. Okay, and I say usually. Okay, so again, when we typically think about solutions, we think of, oh, well, I took some sodium chloride and I dissolved it in water, all right? That's a solid that has been dissolved in a liquid. But that is not the only type of solution. We have several. All right, I can get gaseous solutions where I mix two gases together. This is easy. The air we breathe is a solution. It's a gas in gas solution because the air that we breathe is a mixture of multiple different types of gases. But it's a true solution because can I see anything? No. All right, liquids, I can get a gas dissolved in a liquid. I can get a liquid dissolved in a liquid. I can get a solid dissolved in a liquid. Okay, and again, the solid and liquid, or maybe liquid and liquid too, these are the most common that you will end up dealing with. Now, gas and liquid, how many people have had a carbonated soda? Well, when you first get the soda, if it's in a plastic bottle and you're looking at it, you can't tell any difference. But as soon as you open up that soda, some bubbles start to come out of it. And so while it is under pressure, there's the carbon dioxide that's been dissolved into the soda. And so you can't see that carbon dioxide gas while it's under pressure. Okay, we can get liquid and solid, solid and solid, and we can get gases and solids. So we can get lots of different types of solutions. They're not always as common, and some solutions are much, much easier to make than others, but there's a lot of different types of solutions out there. Okay, now when we talk about dissolving and we talk about how solutions go together, we have to go back to considering intermolecular forces. So when we look at solutions, there's a whole bunch of different things that can be going on. All right, I can get an ion dipole, so something like sodium chloride dissolved in water. My water molecules have a permanent dipole moment to them because they are polar, and my sodium chloride splits up into ions, so we get that ion dipole. Hydrogen bonds, all right, so methanol has hydrogen bonding, water has hydrogen bonding. When I mix the two of them together, I get hydrogen bondings between the solute and the solvent. All right, dipole. If I take two polar liquids and I mix those together, I can often make a solution from there where both liquids have a permanent dipole moment due to their polarity, and so those intermolecular forces will mix and we get a dipole-dipole. Ion-induced dipole, sometimes, not always, but sometimes we can get ionic substances dissolve in something that is typically nonpolar if we can induce a large enough dipole. Okay, this doesn't happen with everything. Like if I try to dissolve sodium chloride into vegetable oil, not going to dissolve, okay? But maybe I can get, something that's a smaller chain to give me some of that interaction. Dipole-induced dipole, again, same thing. Like we have to induce enough of a dipole. So something like water and xenon gas, not typically going to mix, but maybe we could get it to mix if we can induce enough of a dipole into that xenon. And then obviously our dispersion forces, right? If I take two nonpolar substances that both have strong dispersion forces, they're going to end up dissolving. All right, because what is the slogan we use for solubility, for dissolving? Hopefully you remember it from prep chem. It's something dissolves something. It's like dissolves like. Okay, and so we need to have a situation where we have similar forces in order to get them to dissolve in one another. All right, it's like, I don't know, if you go to an elementary school playground and some of the kids might want to play house and other kids might want to play dodgeball. Well, the kids playing house and the kids playing dodgeball, they're doing two very different activities, right? So they may not necessarily intermingle with each other. And in fact, if they try to intermingle with each other, they may not do so very well because those are two very different types of activities. That's not to say that, once they get back in the classroom, they're not all friends. But on the playground itself, during those activities, they're very different. And so they don't lend itself well to mixing together. And so that's what's happening here. as like dissolves like. They have to have similar intermolecular forces in order to intermix with each other. All right, and so when I look at what's happening, now for this, our most common solvent that we use is water. Obviously, we have lots of other different solvents out there. However, water is a very common, very typical solvent. It solubilizes tons of ionic compounds, and there's a lot of liquids that'll intermix with water as well. So water is our most common, but not our only solvent. Especially if you go on to organic chemistry, you'll end up dealing with some other types of solvents. But water is super common. Like when I used to do research, water was not my solvent that I used. I used something called methylene chloride for the most part. And it had to be super dry, so I couldn't have any water in it at all. So water is not the only solvent out there, but a lot of what we do is with water, especially at the teaching level like this, and so we focus a lot on water as our solvent. And so what happens is in any solution, regardless of it being water as a solvent or not, what ends up happening is we've got solute particles become surrounded by our solvent particles. So solute particles are surrounded by solvent particles. Okay. They begin to move through the solution in a solvent cage. Okay, and so you can see I've got a couple pictures here where we've got something surrounded by the solvent. Now, if we are dealing with water, we have a term called a hydrated ion. Okay, so what are hydrated ions? Ions surrounded by water molecules. All right. We also sometimes call this a sphere of hydration. So you can see I've got this hydration shell up here. All right, with water as the solvent there. Okay, and then just to blow up a little bit bigger particulate, here you can see, all right, we've got this potassium fluoride, and so we have our spheres of hydration. We've got our little solvent cages where the water surrounding the ions, where the negative end of water is going to surround the cations and the positive end of water is going to surround the anions. All right, so let's do a couple examples. We're going to look at a solute and two potential solvents and figure out which solvent will dissolve more of the solute. Okay, so sodium chloride is our solute, and our potential solvents are methanol or propanol. So think about sodium chloride. What do you think is going to happen? So sodium chloride, it's an ionic substance that likes to split up into sodium ions and chloride ions. All right, methanol is this little small guy here. Propanol, we've got 1, 2, 3 carbons. I'm not going to put in all the hydrogens. So which one do you think is going to dissolve more of the sodium chloride? The small methanol or the larger propanol? Thinking about, you know, what's going on with the sodium chloride. We need something that is polar. Hopefully you said methanol, because methanol is super small. So that carbon side chain, there's only one carbon there. So that's not going to predominate force-wise. Methanol, hydrogen bonds, it's very polar. When we get to propanol, we have 3 carbons there. So now that carbon side chain and the dispersion forces start to take over the intermolecular forces in that particular compound. And so its ability to solubilize something like sodium chloride is going to go down. And so methanol is going to be our better solvent for sodium chloride. All right, let's think about ethylene glycol in hexane or in water. All right, so ethylene glycol, we've got oxygen, carbon, carbon, oxygen, and then obviously our hydrogens. All right, hexane is a 6-carbon long chain, straight chain hydrocarbon. Water obviously is our little polar guy here. All right, so what do you think is going to dissolve more of that ethylene glycol, the water or the hexane? So think about the 2 ends on the ethylene glycol. You've got those hydroxyls, all right? Are they going to hydrogen bond? Absolutely. And the center portion with those carbons, is that very long? Nah, it's not very long. So ethylene glycol will actually be more soluble in water than in hexane. In fact, ethylene glycol is what is commonly used as antifreeze in car radiators. All right, and then diethyl ether. So diethyl ether, we've got a carbon, bridging oxygen, carbon, carbon, and then of course all of our hydrogens put in there. Now, it's not straight. I'm going to do some carbon framework for you. It actually looks more like this. All right, so it is polar. Now water, we've got our little H2O. Ethanol is 2 carbons and a hydroxyl. So when we look at this, if we think about that structure of diethyl ether, it kind of looks like almost 2 ethanols stuck together, right? So what do you think it's going to dissolve better in? The water or the ethanol? It's going to dissolve better in the ethanol. Okay? So we have to think about the intermolecular forces and how all this stuff goes together. There's a lot that goes into something dissolving. All right, so there's some energetics, going back to thermodynamics. So there's our delta G equals delta H minus T delta S again. All right, so remember that delta G is our Gibbs free energy. Our delta H is our enthalpy. T is temperature. And then the delta S was our entropy. And it's a measure of disorder. Again, you'll do a lot more with this classic thermodynamic equation in 142, but we have to mention it. So whether or not something dissolves has to do with this delta G here, and it has to do with all these things together. When I look at delta H, all right, because we want to get delta G to work out. And so there's some things we have to consider. We have to consider the sign of delta H, because how large delta H is has to do with then what happens with that minus T delta S, all right? Which is why there's more to it than just the enthalpy, all right? The temperature and this disorder also play a part. And if you remember when I lectured on thermo, I showed you that there's endothermic dissolution, or an endothermic reaction, that's right, it was an endothermic reaction that was spontaneous because it ended up creating so much disorder that overpowered, all right? So there's 3 things that the sign of delta H depends on, whether or not delta H or enthalpy is positive or negative, all right? So there's the enthalpy, to break the crystal apart. or to just stir. So this is the solute. Okay, break the crystal apart when we talk about a solid, or the enthalpy to disrupt the solute if it's a liquid. All right, then there's the enthalpy of disrupting the solvent structure. All right, both of these cost energy. So these give us a delta H that is greater than 0 because it takes energy to do these disruptions. Okay, and then the last thing is the enthalpy change to hydrate if we are talking about water. Okay. Okay, the enthalpy change to hydrate the solute. Okay, and so we're looking mostly at solid in water. Okay, so this is dealing mostly with a solid in water. Doesn't always have to be a solid in water though, because again, the enthalpy to break the crystal structure apart of a solid could be the enthalpy needed to disrupt the solute structure. All right, and then when we talk about the enthalpy change to hydrate the solute, we could be talking about the enthalpy change to make a solvent cage around our solute if we're not dealing with water. All right, but because most of what we deal with at this level is a solid dissolved in water, that's why the terminology tends to focus on that. All right, now this last part, the hydration or the surrounding of the solute with whatever our solvent cage is, this is typically favorable, all right, and this usually gives us a delta H that is less than 0. So we get some energy back there. When we are making a solution, delta S is generally positive. All right, because if we think about it, if I've got, that nice tight crystal there, and then I dissolve it, I've got all these ions floating around now. So what's more disordered, my solid crystal or all my ions floating around? Obviously all my ions floating around. Okay, so we've got these three processes. So let's take a look at these in a little bit more detail. And let's understand these three events. All right. So again, we have three events that have to occur. Okay. Let's see here. I put a picture of my solvent. So our first event is going to be the solvent particles are going to separate from each other. Okay, so our solvent particles, you can see from my first picture to my second picture, our solvent particles are going to separate from each other. Okay, so what's happening is we're overcoming our intermolecular attractions. Okay, so overcoming Okay, so we're overcoming those attractions. That takes energy, so it is endothermic. Okay, so I can write an equation. I can take my solvent. All right, so my solvent's all aggregated together. They have some sort of energy like heat. We get solvent that is then separated. And so our delta H is going to be greater than 0. It takes energy. Okay? So our solvent particles are separated from each other. We've taken some energy for that. Okay, the other thing is the solute particles have to separate from each other. Okay, and then involves overcoming intermolecular attractions. So it is also endothermic because that takes energy. All right, so we start off with our aggregated solute. We got some energy, and we get our solute that is now separated. Okay, and our delta H of our solute is going to be greater than 0. All right, so I've broken up my solute, I've broken up my solvent. Now I have to let the two of them mix together. Okay, and so solute and solvent particles mix. All right, now, so what's happening here is the particles are going to attract each other. They're going to build new attractions, solute-solvent attractions. This is favorable. This gives us back energy. All right, so the particles attract each other, and so it's exothermic. All right, so my solute that has been separated plus my solvent has also been separated. All right, is going to give me my solution and heat. All right, and this is our delta H of mixing. And it gives us energy back, so it is less than 0. It's exothermic. Okay, but that's still not the whole story. So a couple things have happened. Well, 3 things have happened. We have disaggregated a solute, we've disaggregated a solvent, and we've mixed them together. But the overall energetics of our solution, the delta H of the solution, looks at all 3 of these things, okay? So we've done the 3 steps that we need to make the solution, but now what's our final energetics of the solution, right? Well, we can get 2 different things, okay? I've got one solution where my delta H of solution is less than 0, and one solution where my delta H of solution is greater than 0. And so that goes back to all these different things added in together tell us what the delta H of the solution is. So this is my exothermic. This is my endothermic. All right, so my total enthalpy change that occurs when a solution forms from the solute and solvent is the heat of solution. So delta H of solution is heat of solution. It's the total okay? That total enthalpy change for formation of a solution. Okay, and so we get delta H of solution is a combination of the delta H of the solute, the delta H of the solvent, and the delta H of mixing. Okay, so all three of those things give us our overall heat of solution. Now, what is this an example of? What does this look like? Hess's law. And why can we do this? Because enthalpy is a what type of function? It's a state function. So enthalpy is a state function, which is why this works. Okay, I can show you a few here. I've got two solutions that are endothermic here, and then one solution that's exothermic. So, you know, sodium chloride, that process is endothermic. Ammonium nitrate, that process is endothermic. Now, if you look at those two, which one is more endothermic? The ammonium nitrate, all right? And so what's interesting is you can actually feel these solutions get colder as they are forming. And in fact, ammonium nitrate does feel significantly colder to the touch than a sodium chloride solution. Okay, and then this one, okay, this is our exothermic solution. Dissolving sodium hydroxide in water is very exothermic. When I was a lab tech at my old high school and I had to make sodium hydroxide solutions on cold days, I loved it because the lab prep rooms were really cold and my hands get cold super easily. And so I loved making sodium hydroxide solutions because I would get it dissolving and I would put my hands around whatever vessel I was doing the solution making in to sit there and warm my hands up because my hands were always cold. So this one's significantly exothermic. All right, so that is our introduction to solutions and understanding the thermodynamics involved with forming a solution.